simulate for much longer time. You can you have a much smaller file size. Parasitics, not parasites, parasitics. We cannot. We cannot really simulate parasitics very well. It's okay. We can do that in switching model, and the switching losses we can only compute in the switching model. So with this, I request we break for lunch, and then we start 2 o'clock with the presentation from Ashish, and then we'll pick this back up after that.
Access, and we have various tools for simulation of applications. I will be focusing on simpler, but we have a lot of tools where we can couple the multi-physics or multi-domain areas into a circuit simulation. So I will focus on more on how we can do the multi-domain simulation, or how we can couple the various domains in the circuit simulation. So I will start with the so the name is it is a simulation driven design methodology. So we are talking about the simulation, focusing on the simulation to develop our entire product. So like there will be some thermal aspects, there will be some stresses on the, so how we will take into all these issues into consideration. So this is a design methodology that we have developed, okay, considering the normal flow or normal process that we design any appliance or any application. So to begin with, just what I am saying, just to share that with you. Now this chart represents the entire cycle of the product development, not the in case of say production, but the simulation in perspective. Now when we start with any motor, how we start is with this tool. Like we focus more on an analytical tool, like sort of Excel sheets. Okay, say for example, we have various methods, say V0 methods. We use and we finalize some geometry for the motor, because there are some the guidelines which is followed for the motor design, which can be implemented in the sort of Excel sheet. So this is a very simple approach, analytical approach, and we do lot of assumptions here, okay, to speed up the our analysis. But we want to overcome the assumptions made here, and that is why we do the finite element analysis. Now here we get rid of the assumptions that we are making. Now when we come into the FE domain, here we define the problem as is. Whatever geometry is there, we import the geometry and get everything here, and we know now the say broad performance, or say some performance like idea we have from ARM expert. So we can have like sort of guideline to verify the finite element analysis solution. Now once we take this into FE domain, we can either take it to we will solve here. We will see the field, we will see the flux linkages, we will see the flux linkages, we will monitor the voltage induced, okay. And once we are done with that, okay, once we finalize the design or optimize the design in this, we will be interested in knowing the thermal and stress on that, say on that motor. So we will take this entire motor into this domain, and if like this is a seamless flow, whatever I am talking, if we use these tools, this is a seamless flow. Within a single click you can take this entire geometry here. Within a single click you can take this geometry here and do the thermal analysis. So that is what the simplicity we have in these tools. Now once we do this thermal analysis, then definitely we will either hook to this motor to the circuit and the load, and that is why the simpler is coming into the picture. So now, when I say this is a bidirectional coupling, okay, it can go back and forth here. I will show that how it goes and come back. Now, this inverter or the controller will be connected through cables. So we have a here Q3D extractor where we can extract the RLC circuit and we can then include it in the main circuit. Then we have a icepack this thing product where you can do the complete thermal analysis of the inverter. Say for example, in inverter you may have fan. So you will be or say for IGBT you will have a heat sink. So how will you simulate all those things and say, check the performance, thermal aspects of that by using icepack. And again this has connection with the simpler. So if you look at the simpler, you are coming from say analytical tool, finite element tool, and this is a finite volume tool, and this is a extraction, and so all this thing is possible in a simpler. So you can see, I will show you how the entire thing or say entire product can be designed using simpler. Now I show like this is a quick introduction of all tools. Now I will concentrate on only few tools here, which are applicable for the drive, say drive application. Okay. Now I started with RM Expert. Maxwell 3D 2D is a finite element analysis. Then I will do the optimization and I will come to simpler. Now the simpler, when I come here, this is what I mean the bidirectional coupling with the. So if you see here, this is a bidirectional coupling with finite domain. Now when at say t equal to 1, this will generate some waveform and this will be fed to motor. This block will go back to AC domain. At t equal to 1, this will be solved, the parameters will be extracted and it will be again fed to simpler. So this is a dynamic, like we are not assuming anything here, that L is constant, R is. So all those are taken as a real time at t equal to 1. And then once I come back here, I will see the load here, what is the load condition. And you can plot the real speed curve or torque curve with respect to time by considering the AC domain. So this is what the tool set that I have for drives. Of course, you can include the fluent and stress analysis here. Fluent is actually a thermal solution, so that can also be included. So these are the applications. Power and drives, transportation. We have drives, power supplies, rail. Now this is a classical example. Now Rakesh sir discussed about electric vehicles in this presentation. So I thought to have this. This is the right forum to talk about. So if you look at this electric vehicle, what are the concern or what are the things that you will be looking at? EMC, EMI, IGBT characterization, efficiency of motor drive, behavioral modeling, okay, of the components, thermal aspect, efficiency and device characterization, and then of course the battery cooling. So these tools addresses all the concerns or provides a solution in electric vehicles. So like these tools, whatever I have presented or I am presenting here, it can be bunched and solution can be formed as per the application. So this is the general tools I am presenting here, but as per your requirement, you can club the tools. So just like few tools I will demonstrate. This is a RM Expert. This is an analytical tool which can address almost all kind of motor. These are the topologies that will be there in the motor. This is possible like all kind of windings. We have a winding editor. What I am giving here is an overview. If you want, you can stop me. We can have discussion. But this is just a quick view, like what all capabilities it has got. We can generate the complete report for the motor. This is an analytical tool again. Then we can take it to FE domain. This is the automatic extraction of the geometry from the RM expert. And then we have all parametric, we have statistical tools, we have Monte Carlo analysis also in that. And these are the optimizers that are available. So depending on your applications, you can select the optimizers from there. Then I am coming to FE domain. So here we will be talking about static, quasi-static and transient solutions. We can do isotropic material, we can simulate isotropic and isotropic materials. Of course we can do optimization here. It has a very strong co-simulation with Simpler. It has a direct link with RM expert, that is analytical tool. And it is, yes, we can take it of course to the stress and thermal analysis. So these are the solvers that it has. So it can solve various problems in this FE domain. This is the technology that we have for meshing. In FE domain, you need to mesh the geometry. So this is an automatic meshing we have in Maxwell. You can simulate the permanent magnets. There will be orientation of permanent magnets. We can do that. We can do the analysis of demagnetization current. What is the maximum current that it can handle? This is a very good dynamic tool that we have, that is called a calculator. And this calculator, like if you are well versed with electromagnetics, you can use this and extract the components from the FE domain. So whatever leakages that we talk about, leakage factors, okay, those are, we are assuming, we are coming from some assumptions. But here, if you go from finite element domain, these assumptions will not be more, it will be more realistic. These are the plots that you can expect. Some Cogging torque you can find out. Flux density in air gap you can find out. And then coming to simpler. Now, what we have done till so far is, we have analyzed the components here. Electromagnetic, thermal, fluid and mechanical, these aspects we know. Now we will connect it to the circuit, sub-circuit or a complete system. So Simpler comes into this, this is the bridge that Simpler addresses. So now in Simpler, it is like I said, it is a multi-domain simulation and it can handle electrical circuit, thermal circuits, like it can handle like whatever PSpice circuit simulation, block diagrams, state machines, and it is well integrated with these tools. We can do characterization. Say for example, in case of IGBT, you will have a data sheet from the supplier or a vendor. So you can directly feed that data into the Simpler, and exact characterization of IGBT will be done. And not only for that, DC-DC converter also can be characterized like that. So that facility is available in Simpler. Simpler can talk with Simulink. This is a bidirectional. It can talk with MATCAD. Okay. You can supply C++. Of course, VHDL AMS is the bread and butter for this. So it is there. State machines, block diagrams, circuit simulators. So this is like a say snapshot of what can Simpler do. These are the models that you can import in the Simpler. These are the some Simpler methodology. We can do the analog digital circuits. We can do the DCS. We can handle the analog controls, mechanics. We have libraries for hydraulics, mechanical loads. We can simulate. These are the some VHDL AMS open library sources that any software will have. This is the power library, like you will have some inverter topologies, converter topologies, control algorithms. We have a mechanical elements library, we have transmission load, rotational load. You can simulate the exact load characteristics in this. So load characterization is another feature of Simplora. This is the SMPS library we have. We have a lot of manufacturers SMPS already included in Simplora. This is a DC characterization that I was talking about. You can use data sheet, test data, and use the characterization tool. And this is what you can expect from Simplora. This is on a single same desktop. You are viewing a circuit, you are viewing blocks, you are viewing a state machines. So utilizing all these three tools, you can simulate the complete problem. You can see here the motor which is coming from Maxwell. So in a single window, you can expect this. These are some examples that we have. This is an inverter drive. So again here you can see state machines we have used. This is the graphical representation. The mechanical elements are put here. This is a wind power generator system. Somebody interested, we can have more discussion on these applications. This is just a snapshot that we can do in Simplora. This is the THD, power factor corrections, that we can use equations, we can calculate THD, and we can do a lot of analysis for THD here. And this is again a motor drive system. This is again hooked to the Maxwell. So these are the block diagrams that are used, state machines are used. So using different tools you can simulate the application. This is what the co-simulation we have with MATLAB and Simulink. So you can directly use this MATLAB or Simulink model, and you can give command from Simplora itself, and it can run into it will go to the MATLAB or Simulink, and it will come back with the feedback. So that kind of simulation is available. So you can do that kind of co-simulation. These are some examples that we have editors. We have editors for C, Spice, XML. You can edit. This is the VHDL MS scripts that you can edit here, and you can use in your project. So another tool we have, that PSpice. This is mainly for the small transformer or say core analysis. We can do this kind of magnetic analysis for the cores, poppings, wires, and we can extract the parameters. We can bring back to Simplora. This is a buck converter example. This is a forward converter, so you are aware. So just I am giving the capabilities that it has. Then we have a Q3, the extractor. Say this is to extract the parameters from the cables that are hooked to inverter controller, and you can then use that, and it is it can definitely this tool, so it can interface with this. This is what I am talking about, the couplings. So I will spend little more time on this, because this is what any industry is expecting these days, because you need not to only do the circuit simulation. They will also be interested in knowing the thermal characteristics, how the stresses are coming, how the heat sink is designed, whether it is sufficient. So all these issues, or say you are using a motor in the circuit simulation. If you use a Maxwell to couple and in the circuit simulation, the approximations that we are considering for the L, for all the parameters, like you will have a dynamic coupling there. So that is the advantage. So we are overcoming the assumptions that we are making while simulating. So this is what is now the losses are mapped. the whatever losses are there, it is mapped in the thermal analysis, and we can get the temperature feedback from the thermal analysis, and we can come back to the motor, adjust the pH curve, adjust the resistances, and do the simulation again. So this kind of feedback you can expect in the Maxwell. This is the one example. This is another, that is Maxwell thermal coupling. This is a solenoid example. So you can view the thermal aspect of it. This is the IGBT inverter, and that is what I was talking about, the fan simulation. So here is a fan blower, and that is what you can expect the flow out of it, and what is the cooling capability it has got, that can be simulated in the ice pack. And all this tool can be coupled to the Simplorer. So Simplorer is like a mother, and these are the like child giving the feedback, and they can talk each other. So this is a IGBT inverter design. If you see here, this is what the thermal is connected. This is now Simplorer domain. So here if you see, the thermal domain is hooked here in the circuit domain, and if you see, this is a FE domain that is hooked in the again circuit simulation. And this will be like it will go every time step. This is a this is a transient analysis. Every time step it will go here, come back, see the condition, see here conditions, and load, and then generate the plots.
So it takes a lot of time for simulation result to come out.
Alright, it will take time, but you will get the correct.
So what is it Simplorer can do alone?
Simplorer is like any PSpice if you have. It will have all the
electronics.
Then it will have characterization, IGBT. So all power electronics, whatever you are doing with PSpice or Spice,
Can be done.
or Simulink, or Saber. So all that is possible. And not only that, you can get the models, the ready-made models from there. Say for example, if you see that there is some model is not there in Simplorer, directly you import the model as it will be there, and you can modify. That is why I show you the editors.